The purpose of this lesson is to explain what asymptotes are and to show how you can find asymptotes for particular graphs. First and foremost, as you can see from the definition here, an asymptote is a line. And it's a line that a graph gets closer and closer to but never touches. And we can see this in an example here. One of the most common examples would be the graph y equals 10x. And the graph is shown here in blue. It's a graph of y equals 10x. But it behaves in a peculiar way as the angle gets towards 90. Let's just have a look. First of all, the tan of 0 is 0, so 0, 0 is on the graph. You get up to 45 here, the tan of 45 is 1, so 45, 1 is on the graph. But once you go above 45 and start getting closer and closer to 90 degrees on the x-axis, the tan gets very, very large. And it gets very large very quickly. And by the time you actually get to 90, the tan is undefined. So there is no value for tan of 90. And so if you go straight up from 90, obviously we can never ever reach the graph. So just before 90 it does have a value, as you can see from the blue here, and just after 90 it starts off down here again. So we've got a situation where the graph is not defined at 90, but it is defined at both sides. Or another way of saying it is the graph gets closer and closer to this red line here without ever touching it. And that red line is called an asymptote. So as I said in the definition, a line that the graph gets closer and closer to but never touches. On the graph we have here, there are two other asymptotes shown. There's an asymptote at x equals 90, also at x equals minus 90, and x equals 270. Now there are other examples of asymptotes, and in this function here, this is called a rational function. We can work out where the asymptotes are as well. And before we do, let's just remind ourselves of another way of we can look at asymptotes. If you look at the graph here, the asymptote is the red line again, and it's basically a line the graph never touches. We can also think of it as this. We can think of it as a value of x which has no corresponding value of y, where y is undefined. The value of x we're talking about here is 90. So when x is 90, y is undefined. And that's a nice way of thinking about it, because if we go back to our function here now, where would the asymptotes be? Well, if we can think of a value of x which makes y undefined, which makes this here undefined, well then we've got an asymptote. Usually this happens when below the line in a fraction is 0. If the value below the line is 0 and you're dividing by 0, that's an undefined quantity. So that's how we find out where the asymptote is in this case. So x minus 2 is 90. Sorry, is 0, which means x equals 2. And it's as simple as that for finding the asymptote. When x is 2, the value of y under the line is 0, therefore y itself is undefined. And we call this the vertical asymptote. So there is a vertical asymptote at the value x equals 2, just like in the tan graph there was a vertical asymptote at x equals 90 degrees. Now there can also be horizontal asymptotes, and as you can imagine, if a vertical asymptote is a value of x for which y is undefined, well, horizontal means a value of y for which x is undefined. This basically amounts to getting the limit of y as x goes towards infinity. That is, get a value of y for which x goes towards infinity for which x is undefined. So we get the limit of x plus 6 over x minus 2. You sub in infinity above and below just to see if it works out, and it doesn't give us any clear value. I mean, we still get infinity over infinity, which is again undefined, so we have to go further here, and there's a technique here for working out this, and it involves dividing above and below the line by the highest power of x. X plus 6 over x minus 2. So what I mean by that is we divide above and below the highest power of x is 1. I mean, there's no x squared anywhere, the highest power is 1, so it's just x over x, 6 over x, x over x, 2 over x. And that gives us the limit as x goes towards infinity, x over x, which is 1, plus 6 over x divided by x over x, 1 again, minus 2 over x. Now we can start making sense of this, because if you think about it, if x is infinity, as a matter of fact, I don't even need to write down this again, because if x is infinity, anything divided by infinity is 0. We're divided by a very large number, so you divide by something by a large number, it gets very small, so infinity is the largest, so it becomes the smallest, which is 0. So we can do that. That becomes 0, and that becomes 0. So we're left with 1 over 1, which is 1. So the limit is 1. So we say that the asymptote is at y equals 1. So y equals 1 is the y value for which there is no value of x. X is going towards infinity. So we can put all that together, and we now have the horizontal and vertical asymptote for that graph. As we saw earlier, the vertical asymptote was x equals 2. So before we start drawing the graph, we know immediately where the asymptotes are. There's an asymptote at y equals 1, there's y equals 1. So if we drew a line straight across there, that's one of them. And as we saw earlier, there's another asymptote at x equals 2. So if we dot in 2, there's x equals 2. So there we have it, a horizontal asymptote and a vertical asymptote. Again, these are two. We don't know what the graph looks like yet. We're not concerned with that in this video, but we do know that when we do get the graph, it will get closer and closer to those two lines without ever touching them. And that's what we mean by an asymptote.